Hello and welcome back to the course of rock mechanics principles. This is session 5.2 and it will cover two tests here on rock materials hardness and on wave velocity in rock materials. We will start with the measurement of rock hardness using the Schmidt rebound hammer to measure the Schmidt hammer rebound hardness. Schmidt hammer rebound hardness test is a rather common test method, not only used for rock testing, but also for concrete and structure testing. The method has been standardized by the International Society for Rock Mechanics and the American Society of Testing Methods. The RSIM suggested method and the ASTM standard testing method for the Schmidt hammer rebound hardness are listed here. The test described here follows the suggested methods. To do the test, we will need to have the Schmidt rebound hammer. Schmidt rebound hammer is a spring-loaded piston. When the piston is released and impacting a solid surface, the piston rebounds. The degree of rebound represents the hardness of the surface, which gives a hardness number. The typical Schmidt rebound hammer are shown on the right. The one below has a digital readout. On the market, there are two types of Schmidt rebound hammers available, the L type and the N type. The L type is for laboratory use or use on flat surface, including on concrete wall, beam, and columns. This is the common one, and the test described here is based on L type. The N type is primarily used at field, on site, on rough rock surfaces. Schmidt hammer rebound hardness tests in laboratory are usually on a rock block or on a core end with a flat surface. Specimen should be intact and homogeneous, and at least 100 mm thick and 50 mm side length or diameter, and firmly secured and fixed. Hammer should be held at a right angle to impact the tested surface. After the impact, the hardness reading is shown on the side of the hammer. At least 20 rebound values per sample is required. If it is done on a large block or on a concrete surface, the impact should be separated by at least 25 millimeters. The test is very straightforward, and you can do many impacts on a large block or a larger surface, as long as there is sufficient space. However, there are possible human errors in testing. For example, not holding exactly perpendicular, or the hammer not rebound properly. We therefore usually eliminate the measurements of two end 10%. That is, the top 10% and the bottom 10%, and use the middle 80% as valid results. Test report. Apart from giving tabulated Schmidt-Hammer rebound hardness values obtained from the test, the average hardness values and the range should be also given. Preferably, the test hardness values are also presented in the histogram. The report should also include descriptions on the Schmidt-Hammer used, for example, type L or type N or other types, and its calibration history. Sample descriptions must be provided in the report, including rock lithology, sample locations and depths, sample shape, dimension, water content, foliations, or any anisotropy. Orientation of hammer axis with reference to the rock anisotropy features must be clearly stated. It is always good to have photographs of specimens and the test apparatus. In the rock mechanics class, section 2.1, we have learned that we can estimate rock material strength from the Schmidt rebound hardness. And the correlation is shown by this chart here on the right. As illustrated on the chart by the dotted line, if we have the Schmidt hardness of 48 obtained by vertical down hammering on the surface, say a homogeneous and isotropic sandstone block with unit weight of 26 kN per cubic meters, then the estimated uniaxial compressive strength of this sandstone is 120 megapascal. Please note that on the lower part of the chart, the orientation of a hammer axis with reference to rock anisotropy features is important in determining the hardness and is affecting the strength correlation. The next test we are going to learn in session 5.2b is to measure sound wave velocity by ultrasonic pulse transmission techniques. The test method is part of the suggested methods proposed by the International Society for Rock Mechanics and Rock Engineering. It is documented in the ISIM suggested method for determining sound velocity by ultrasonic pulse transmission technique of 2014. The equipment required to perform ultrasonic wave velocity measurements is the ultrasonic velocity tester or the ultrasonic pulse velocity tester. The ultrasonic velocity tester system include the signal generator and display unit that generates ultrasonic wave signal, record and display wave traveling time. It is connected to the wave transmitter and the wave receiver transducers. Most of the ultrasonic velocity system can produce both P wave and S wave. therefore can measure p-wave velocity as well as s-wave velocity. The tester usually comes with a calibration specimen for regular calibration of the testing system. A typical ultrasonic velocity tester system is shown on the right. The specimen sandwiched between the transmitter and the receiver is a calibration specimen marked with 42.5 microseconds. That means if you're testing with this specimen, you should read the time traveling is 42.5 microseconds. To use this to calibrate the system. Let us go through the procedure of taking measurements using the ultrasonic velocity tester. First, we need to have specimen with sufficient length. Usually a long cylinder with length greater than 100 mm. The end surfaces should be flat and smooth for good contact with the attaching to the transmitter and the receiver transducers. Couplant materials like petroleum jelly, grease, pasta can be used to ensure good contact between the transducers and the rock surface. Specimen length is measured and recorded to the accuracy of 0.1 mm. Then the specimen is sandwiched between the transmitter and the receiver, as shown on the illustration. Using the signal generator and display unit, you can generate the ultrasonic pulse wave. The wave is then transmitted through the rock specimen and received at the other end. The traveling time is recorded and displayed by the signal generator and display unit on the top. As you have already measured the length of the specimen and also have measured the wave travel time through the specimen in the test, you can easily calculate sound wave velocity, which is the specimen length or wave travel distance L divided by the wave travel time T. If the ultrasonic wave you used in the test is P wave, then the velocity you get is the P wave velocity. Vice versa for the S wave. It is required, as suggested in the ISM suggested method, that at least 3 measurements on 3 specimens should be done for 1 rock sample. Test report should have tabulated specimen length and the wave travel time and the calculated wave velocity to the nearest 10 meters per second. Average wave velocity for the sample should also be presented. The report should also include descriptions on the ultrasonic wave tester and the calibration history. In the report, sample and specimen descriptions must be provided, including rock lithology, sample location and the depth, specimen shape and the dimension, water content, foliations and microcracks inside the specimen, together with photos. To end the session of wave velocity, here I show you the P and SO velocities of some common rocks. You can see that the velocities can be in a rather wide range. This is the end of the session on measuring Schmidt-Hammer-Lubin hardness and the ultrasonic wave velocity in rocks. Next session will be on uniaxial and triaxial compression tests. Goodbye and see you later on next session.